All right, welcome back, everybody. So this is section 2 for the precise definition of a limit. Okay, I want to start today by thinking back to section 2.2, really. When I said, okay, the definition of a limit is basically like saying, I'm going to get closer and closer and closer to something. I'm going to let x go closer and closer and closer to something to see what happens with the y values, right? As x gets closer and closer to 1, meaning I'm going to plug in 0.9, 0.99, 0.999, and so on and so on and so forth, until I see a pattern within the y values, right? Now, that's kind of a very vague statement, right? To say, until I see a pattern. Like, how close does it really have to be? Does it, is it going to be, sufficient to say, oh, it's close enough? What's enough? What is close enough? That's what we're going to be looking at today. How close is close enough? How close do you have to put your x value? 0.9, 0.99, 0.999. How close do you have to put your x value to make your y value close enough? And what we're going to do today is make that close enough an arbitrary value. Okay? We're going to make it like a variable. And we're going to say, okay, we're going to make it the y values turn out to be like 0.1. And then we're going to make the values turn out to be like 0.01. And then we're going to make the values turn out to be epsilon. We're going to make it, this is what we're going to do today is called the delta epsilon definition of a limit. Basically, it's saying that I'm going to take my x values so that it's closer and closer and closer to the value of the limit. Like as x approaches 1, I'm going to make it closer and closer to 1, right? How close to 1? Delta close. Why do we make it a variable? So that it can be arbitrary. So we can make it closer than we, how close enough? Closer than we even think is possible. Okay? Whatever number we think is smaller enough, we can put a number in front of that, right? So we're going to make it closer and closer and closer to 1. How close to 1? Delta close. Make it arbitrary. Okay, well, if it gets closer and closer and closer to 1, what's going to happen? Well, it's going to come out, the y values are going to come out to be some number. And that number is going to get closer and closer and closer to the actual value of the limit. How close? Epsilon close. Okay, so we're going to have to choose a delta, close enough delta, and we're going to see, okay, where does that epsilon come out to be? That's really what we're going to be looking at today. Okay, enough of me talking. Let's go through here. The intuitive definition of a limit from section 2.2 is inadequate for our formal purposes. You know what's funny? When I first started teaching this last year, I liked to go onto the books website and look at some of their videos. And this video is hilarious. Because this is going to be a very proper way of doing something. We're going to do some proofs today. Yeah, I know. We're going to do some algebraic proofs. And what we're going to be looking at today is a very, very formal way to write these limits. It's a very formal way. So in the video, it's so funny. He's like sipping tea and has a bow tie on because he's trying to be really formal. Yeah, he's really funny. But the intuitive definition of a limit in section 2.2 is inadequate for our formal purposes because such phrases as x gets close to 2 and f of x gets closer and closer to L are too vague for our purposes. We were just kind of like, we're seeing where it's going and we're just going to assume that it goes there. Now we're not going to assume anymore. We're actually going to prove that those things are. Like, let me show you what's going to happen a little bit later on. Like, we're going to do this problem, maybe if not today, then another day, then whenever we do take 2 of this. I'm going to say the limit as x approaches 3 of 4x minus 5 is 7. Could we do direct substitution there? Of course. We don't even need to know that it's 7. Because we can do direct substitution. Well, why can we do direct substitution? Why? We're going to prove it. We're going to prove that it actually goes to 7. Okay? So I am going to say, okay, as x gets closer and closer to 3, I'm going to prove that it actually goes to 7. How am I going to do that? Well, let's jump back here. Okay? So what we're going to be doing is we're going to prove conclusively that these limits are what they are. Like, for example, we had this back in section 2.2, we had these 2 examples, right? And we said, okay, we found in our calculators Or we found by way of just plugging and chugging that this was going to be equal to 1/10,000, or this was going to equal to 1, right? Now, to motivate this process, to kind of initiate this process, we're gonna examine this piecewise function. F of x is equal to 2x minus 1 if x is not 3. So everything other than 3, f of x is 2x minus 1. If x is 3, f of x ends up being 6. Now, what is our intuition? Our intuition is that as x approaches 3, then I know that 2x minus 1 is going to be what I'm looking at, right? Do I care that at 3, f of x is 6? Do I care that at 3, f of x is 6? No. Because remember, in a limit, I only care about what's happening around that value, not what's happening at that value. Okay, so intuitively it's clear when x is close to 3 but not equal to 3, f of x is close to 5. How did I get 5? Plug in 3. Direct substitution. 2 times 3 is 6, minus 1 is 5. Right? So I intuitively know that the limit as x approaches 3 of this piecewise function is 5. Now, to get a more detailed information about f of x, about how f of x varies when x is close to 3, we ask the following question. How close to 3 does x really have to be so that f of x differs from 5 by less than 0.1? So I'm giving a value to it. I'm saying, okay, I want f of x to end up being 0.1 away from 5. So what's the range of values that it could be? Well, it could be all the way up to 5.1, or it could be all the way down to 4.9. Remember, because we've got to look at it from both sides of the spectrum. So it could go between 4.9 to 5.1. So what we're going to be looking at here is, okay, how close do I have to make my x values so that it goes between 4.9 and 5.1? Right? The distance away from x to 3 is notated by this absolute value of x minus 3. Because isn't distance absolute value? Like that's our definition of absolute value, right? Distance from 0. So I can really show distance by using absolute value. Okay, well, the distance from x to 3, meaning, maybe it's a better way to call this the difference from 3, right? I'm talking about the difference away from 3, right? And I'm taking it absolute value because I don't care about left side, right side, right? Remember, when we're taking a limit, we're examining it from both sides. It's kind of like sandwiching it in, right? When we take a limit, we're looking at it from positive end and negative end to see where it's going to go to. So that's why I use absolute value here. I'm talking about the absolute value of x take away 3. Meaning, if I keep plugging in x values, 3.1, 3.001, 3.0001, 3.0001, I'm going to be making those distances smaller and smaller and smaller away. Like, for example, 3.1, if I plug in 3.1, then my distance away is 0.1. Okay, my distance away is 0.1. Now, when I calculate that, the distance from f of x to 5 is noted by this, f of x minus 5. Okay, I know the final limit is going to be 5. I'm always going to be telling you what the final limit should be. Sometimes I don't even need to tell you because you can use substitution. But I'm going to be telling you what it is. The final distance from f of x to 5 to the final limit is notated by this, the absolute value of f of x minus 5. So our problem is to find a number delta. That's delta. Okay, this is delta. The Greek letter, and actually the lowercase Greek letter delta. This is uppercase delta. This is lowercase delta. It's kind of like a squiggly D. Right, there's delta. Kind of like a D with a squiggle on the top. Okay? That's delta. What we're going to be doing is saying, okay, we need to find a delta. What does delta usually represent? Like back in slope days, we talked about this. Changing, right? Oh, that makes sense. The change in our x value, okay? The difference in our x value. So we want to find a delta, a difference of the x value, small enough so that their outputs only differ away from 5 by 0.1. That's what we're asking here. If the absolute value of x minus 3 is greater than 0, then x is not equal to 3. So an equivalent here is the difference away from 5 is less than 0.1, right? The final output here that I'm going to get has to be less than 0.1 if x is between 0 and delta. X minus 3, the absolute value of x minus 3 is between 0 and delta. I want to make that number smaller and smaller and smaller. How small? Delta small. Now, let's continue on. Notice that if we have f of x minus 5, let's jump right here because I'm going to reference this in a second. If we've got the difference between f of x minus 5 here, do you all agree? Well, our piecewise, it was 2x minus 1, right? That was f of x. So what's the difference here? Well, I'm going to take this and plug in 2x minus 1. Okay, f of x was 2x minus 1. Well, let's reduce that a little bit. That's 2x minus 6, which is really, now, this is an intermediate step here that I wish they would have written. This is the absolute value of 2 quantity x minus 3, right? Now, if that's 2 quantity x minus 3, since the 2 is positive, I can pull it out in front of the absolute value. Okay? That's why this 2 comes out front. Now, is there another place where you see the absolute value of x minus 3? Right here. I never used that within this calculation that I've been talking about. Okay? So what your goal is to try to use the y values to see the output, to try to see if you can manipulate it to look like the difference in the x's. See right here. So right here. Now, the absolute value of x minus 3 was less than 0.11 divided by 2. That's a statement right here, that 0.005. Now, if we put a 2 here, we put a 2 there, that's equal to 0.1. That is, here, this 0.05, that is the difference away from f of x. To make it come out to be less than 0.1, I've got this 0.005. X has to differ from 3 by 0.005 to make it come out to be true. We can find it algebraically, but we can also find it graphically. We can find it algebraically, but we can also find it graphically. Now, take a look at what it looks like graphically. Let me jump. Oh, where'd it go? Let me jump down to here. There. So, what does this look like graphically? Well, what I'm going to do here is I have some function, and I want to prove that the limit is going to go to some value L. And to do that, I'm going to choose an epsilon. I'm going to say, okay, the function is going to go to L. And how much is it going to differ away from L? Epsilon. Epsilon is the lowercase, that's sigma. I think epsilon uppercase looks like that. Epsilon lowercase is just a rounded out. It's kind of like a backwards 3. Okay. So it's going to differ away from the limit by epsilon. And what we're going to do is say, okay, look at the function. Look at the function. And we're going to say, okay, look, this is my upper boundary. This is my lower boundary. I know that it's got to differ between those two values. Okay? The limit as x approaches a from those two values. Now, take a look here. I want to choose the closer of the two values to make it to be close enough to epsilon. Okay, I'm going to choose the closer of those two values, the closer of those two boundary lines. I'm not going to choose this one because this one's farther away. I want to choose the closer of the two boundary lines. And you know what this is actually going to be? Let's take a look at this diagram. This right there, that's going to be your delta. Okay, that's going to be your delta. That's going to be your difference away from x that you want to choose. Okay. Now, how do we find that? Well, we found it algebraically in the last example. This, we're finding it graphically. If I know the function, and I know what the y values need to be, like in the last problem it was 0.1, If I know the function, I know what the y values need to be a difference in, well, then all I need to do is find intersection point, choose the closer of the two, because I want to restrict my boundary lines just a little bit more than necessary, rather than less than necessary. And then figure out that's going to be your delta. Your difference away from your x value, that's going to be your delta. Okay? And what the process is saying, okay, if I choose my delta to be smaller and smaller things, that's going to narrow my focus to be smaller and smaller in my epsilons. Okay? So let's take a look at this example here. I know that was a lot of me talking. I saw a lot of dozing off faces. But this, and I don't want to show that diagram just quite yet. Okay. So this is, I'm going to use this example to kind of demonstrate everything that I was talking about just a second ago. Take a look at that function, x to the third minus 5x plus 6. Now, it's polynomial, right? So if I wanted to find the limit as x approaches 1, I can just plug it in, right? I can just plug it in. I can say that f of 1 is 2, right? So the limit as x goes to 1 of x to the third minus 5x plus 6 is just equal to 2. 1 minus 5 plus 6. Now, what I want to do is say, if I want to find a delta, or what I want to do is find a delta such that the y values are within 0.2 of 2. I'm going to find a delta such that my epsilon is 0.2. Epsilon is the difference away in the y values. That's my epsilon there. Okay, if my epsilon is 0.2, I want to find a delta that's going to make me stay within 0.2 of my y values. Here's how we do that. Take a look. Take a look here. If I want my delta to be if I want my distance from 1 to be less than delta, then this needs to be true, right? This absolute value of x to the third minus 5x plus 6 minus 2, because wouldn't we all agree that's the difference away from my outputs to 2, right? I want that to be less than 0.2. Where did I get that 0.2? It was given to me within the problem. I always have to give you the epsilon, and if I don't give you the epsilon, it's a proof. So I'm giving you the epsilon of 0.2. Now, this is an absolute value inequality. Remember back to our Algebra 2 days. Isn't that a less than, right? Less than symbol. If I've got a less than symbol with my absolute value, that's going to be an and inequality. So that means it's going to be between negative 0.2 and positive 0.2. It's kind of like a bounded inequality, which makes sense. Thinking back to our graph, it's going to be they're like boundary lines. Okay. Well, let's add this 2 over to the other side, because I want to keep this as like an intact f of x. I want to keep that f of x in there. So let's add 2 to the other side. Actually, to all sides, because this is a compound inequality. Well, negative 0.2, I'm going to add the 2. I get 1.8. And this is 2.2. So I want my boundary of my function, I want the outputs of my function to be between negative 1.8 and 2.2. I need to find my delta. I need to find my x values that will restrict me to being in between 1.8 and 2.2. So we go to our graphing calculator. We figure out what those x values are going to be. Oh, there's your faces. Sorry. So what I'm going to do is I'm going to go into my y values, and I'm going to put in my function. X to the third minus 5x plus 6. And over here, I'm going to say, okay, I want it to stay between, I want the y values to be between 1.8 and 2.2. Now, that's not a very wide range, is it? You know, that's only 0.4. So when I go to hit graph, when I go to hit zoom 6, it's almost going to look, oops. If I go to hit zoom 6, It's almost going to look like the same line in here. There's my cubic function. There's 1.8. There's 2.2. What I need to see right here is what's going on right here. I want to see what's going on right there. So remember that you could do this in your calculators. Do you guys know about Zoom box? Can I hit Zoom, please? Don't freeze. Come on now. My calculator's even like, dude, this is too much for today. Look at that. My computer didn't freeze, just my calculator froze. Okay, now is it better? Oh, there we go. Did you guys know you can zoom box? Zoom box, that's zoom 1. You're gonna like trace along and then hit enter and open up a window. Like if I box this, I'm gonna go down and over. That's gonna like make that my window screen. That's what zoom box does. Okay, so what are we seeing here? Okay. Here's what we're seeing. We're seeing the function go by. This line is my 1.8. This line is my 2.2, right? And I know 1 is somewhere in between here, right? Is somewhere in between there. What I need to find is this point and this point, and see which one gets me closer to 1. Okay? I need to find the blue point, I need to find the red point, and I need to see which point gets me closer to 1. So let's calculate that. Second, calculate. Let's do the intersection point, choice 5. It's first curve, second curve. I'm going to go the upper line. I'm going to do left side boundary first. Guess, whatever. So here is my first intersection point. Okay. Here's my first intersection point. My second intersection point, second calculate, intersect. First curve, enter. Second curve, good. I'm on my bottom line now. 1.12. Do you notice how my x values are in between? Or my 1 is in between my x values that I found here? That should always be the case. If you didn't, then something's wrong with it. Okay. Now, I've got 0.911, and then 1.12. Okay, I've got 0.911 and then 1.12. I need to find which one of those is closer to 1. So let's see. I take 1 minus 0.911. We'll round to the nearest hundredth. 1 minus 0.911. And that's 0.89 or 0.089. And then over here, this is going to be 1.124 minus 1, right? Because I'm going to find the difference away from 1. So this is 0.124. So which value got me closer to 1? The first one, the left side boundary line. Okay? This value gets me closer to 1 because this is a less difference away. And you know what? That is going to be my delta. Okay? Your delta is going to be whatever gets you closer to 1. Okay? Your delta is going to be whatever gets you closer to the value that you're trying to get to. I don't want to choose this delta because that's going to be outside my restriction. Mr. Harold.
I heard delta and I just had to pop in.
We're doing some great stuff here today. I'm getting some great looks from my students.
Oh yeah, they just look so intense.
Did you need me, Frank?
We all need you, Mr. Lambert. I'll catch up with you later. Okay. All right, no problem.
You sure you don't want to take her right now? She can just run, just start running and she'll catch up.
No, I don't want to make her get up. So. All right, thanks.
Yep. That was so funny. I'm looking out and you guys are like. most boring lesson of the year. So again, what am I doing here? I'm choosing an x value. I'm choosing a delta value, which is a difference away in my x values that's going to get me close to 0.2 in my difference in the y values, right? We took a look and we said, okay, I want my y values to come out to be 0.2 away from 2, because I knew the limit had to be 2. So I went on the upper side and the lower side. That means 1.8 to 2.2. I'm giving myself like a range of my y values that I want to fall between. And I need to find the x values that are going to make that happen. Now, you're choosing one value of delta, okay? That's why I didn't choose this, because I need to choose a singular delta value. I need to choose a singular delta value, which is going to make me fall between those two epsilon values. A singular delta value. That's why I choose the closer one. Because if I chose the bigger one, that would give me outside my boundary on the other side. Like if I chose my delta to be 0.124, that means that I could go successfully on my one side, but on the other side, I'm going to be outside of my epsilon range. I'm not going to be within 0.2 of 2 on the other side. So if I go on my smaller end, I'm going to say, okay, it's going to be just enough on my one side, and it's going to be closer than what I actually need on my other side. So I'm kind of like hedging my bets a little bit. I'm saying, okay, I want to be closer than I need to be, so I'm going to choose my delta that's going to be closer than my other delta. Okay? Let's save the proof for tomorrow. Does that sound good? Yeah, I've already had some people fall asleep on me today, so let's save the proof for tomorrow. Sound good? Relax your brain.